Alrighty. Okay, so for this problem here, we're going to be doing problem 1.2, which is using the same diagram as 1.1. So in this problem here, it's two solid cylindrical rods AB here and BC are welded together at B, right here, loaded as shown, knowing that D1, which is the big one, is 50 mils, and D2 is 30 mils. Find the average normal stress at the midsection of rod AB and BC. Okay, so the first part with this problem, over here it says 300 mils and 250 mils. Again, don't worry about that. You don't have to worry about that. It says the midsection. Don't worry about that. The stress acts in the entire section. So this whole section and this whole section. So when it says find it at the midsection, don't worry about that. That's actually nothing. Alrighty, so now I had pre-done the problem. Okay, so let's just explain what's going on here. So we're looking for stress AB and stress BC in sections AB and BC. We have D1, which is 50 millimeters, which is here, and D2, which is here. Next we have FB, which is the force acting at B, and FC, which is the force acting at C. So now we got to figure out what our stresses are. Okay, so first thing we're going to do is we're going to start with this section here. So the reason why I'm starting here is because this part here, I didn't draw it, but it's connected to a wall of some sort. So this is a free end, so only the one force is acting on this. So again, if I were to take this for an example, I try to pull on this like so, with my hand being FC. This is the only force acting. This is not considered, FB is not considered because we're not at that joint yet. So first thing we want to do is we want to find out, we're going to use this formula here, so we need A. And the only way we're going to find the area is if we solve for the area of a circle again, so a cylindrical rod. So AC equals pi D2, which is the diameter of the small section, squared over 4. So first thing we're going to do is we're going to use the diameter. So our diameter is 30 mils. I convert it into meters because it's easier for me to go about with the kilopascals and everything. So first thing we got to do is convert it into meters just so everything makes sense. So 30 mils is 0.03 meters. So once we solve that, it gives us 706.86 times 10 to the negative 6 meters squared. Really weird number. Don't have to worry about it. Just, that's the answer that got popped out. Next, we're going to use the normal stress formula, which is stress equals force over area. So I put in the variables. So we're looking for BC, FC, AC. So it's great. We don't have to rearrange the formula. It's already in the right state because we're looking for sigma BC. Yeah, this is a sigma, by the way, in case you're wondering. My sigmas look like that. So first thing we do, FC, which is 30, which is this force here acting, over AC, which is what we solved earlier, will give us the stress. I made a little mistake there. So it's 42.44 times 10 to the power of 3 kilopascals. Okay, so a little note here on what I'm doing. So I have a kilopascal and I have a meter. Usually you would have 30,000 newtons over 706.86 times negative 6 meters. So that would equal a newton, or a pascal, sorry. So what happens is because I'm using a kilopascal, I'm using the pascals, so my answer is going to be in pascals. So because I'm doing that, basically what happened is the answer is 42.44 times 10 to the power of 3 kilopascals. Well, it's still not, we could still convert that into megapascals. So that's what I did here. So I got rid of this times 10 to the power of 3, and I just put a megapascal down. So kilopascal times 1,000, which is what that is, will give us a megapascal. Or I could have broken it down to 30,000 newtons, which would have given us 42.44 times 10 to the power of 6 pascals, which again is megapascals. So here's your answer for the first section. That's the maximum stress that this section could hold before it explodes, kind of deal. So now we're going to go to number 2. So Now we're going to do AB, which is the diameter D1. So again, same formula over here. Nothing changes. We're just figuring out what the area is. So I used a different script for this section here. So I took the 50 mils and I just said times 10 to the negative 3, which is a meter. So 1 millimeter is 1,000th of a meter. So you could also write it in like that or like that. It doesn't matter. It's the same thing. Well, like this one's 30 and this one's 50, but different ways of showing it. So this answer would be 1.96 times 10 to the negative 3 meters squared. So on this section here, like I said previously, so at C we're pulling down here, and then we're also pulling up here. So there's two forces acting on this section. This section there's one, and this section there's two, 1 and 2. So we have to add these forces together. So 40 kilonewtons plus 30 kilonewtons is 70 kilonewtons, and then we have the original in meters. So what I did here was I explained it over here, but I converted the 70 kilonewtons into 70,000 newtons. So I multiplied that one by 1,000, which gives me this number, 70,000 newtons. You divide those two, again, same formula here. Divide those two, will then spit out this number here. So 35.71 times 10 to the power of 6 Pascal. So I explained it over here, but I did it a different way this way. So this is Pascals, but we want it in megapascals, and megapascals is to the power of 6. That is why I use engineering format, because if it was 3, it's kilopascals. If it's 6, it's pascals, or megapascals. So here the answer kicks out to 35.71 megapascals. If you have any questions, please leave a comment. Let me know. Hopefully you enjoyed the video. Thank you.